Loudness and loudness level part 2. Loudness is a perceptual unit in zones that comes from perceptual experiment. Loudness level is defined via a 1 kilohertz reference where phone is equal to dB SPL. So at 1 kilohertz tone, the dBs, SPL and the phones are the same number. If you measure loudness ratings with a 1 kilohertz tone, then we can relate zones and phone. Okay, so phones are sound loudness level and zones are loudness. We have a loudness curve here. Loudness level in phones, that's the same as SPL in dB at 1 kilohertz. You have first axis -20, 0, 20. It's a normal first axis physical level. And then we have the loudness perceptual level in loudness zones. And the second axis is logarithmic axis, 0.110, the same distance between. In this coordinate system, there's a linear relation, if you graph it, between loudness in zone and loudness level in phones and loudness in zones. You use Stephen Powers law. Stephen Powers law, you can say it's the loudness is 2 raised to level minus 40 divided by 10. And if you put an exponential, the loudness is an exponential function of loudness level, the SPL level. Yeah. And if you put an exponential function in a simple logarithmic paper with the first axis normal and the second axis logarithmic, you get a line. You can say here arbitrary reference. One zone is same as 40 phones. And even more here, clear here. And if you raise your loudness level in phones, that means the SPL in dB at 1 kilohertz. T dB increase corresponds to double loudness. It's easier to understand. So when you add 10 dBs at the loudness level, you get a double loudness. Okay. Yeah. And therefore, if you graph it in a simple logarithmic paper, you get a straight line. Loudness normal hearing. Yes, you can say normal hearing listeners. 20 dBs change in level is 4 times louder. 10 dBs is the same, 2 times louder. 20 dBs is 4 times louder. 30 dBs is 8 times louder, and so on. How about hearing impaired listeners like me? Yeah, you can see the curvature below, for instance, 60 dBs loudness level, it will slope faster down than the normal hearing curve, which obeys Stevens Powers law. Yeah, and I have to mention Stevens Powers law. You can also say impact listeners, hearing impaired listeners. 20 dBs change in level is 20 times louder in an area less than 60 phones. So if you increase the loudness level, you just suddenly, if you have hear impairness, the sound is just growing up faster. That is called loudness recruitment. Loudness grows much faster compared to normal hearing listeners. Dynamical range in hearing impaired listeners. Smaller dynamical range in hearing impaired listeners. Against Stephen Powers' law, you can say the loudness is a exponent potence function of the intensity, but it can also be written as 2 raised in L minus 40 divided by 10. So it's an exponential function. Yeah. Where L is the SPL value. Loudness and duration. Loudness depends on sound intensity and frequency. Loudness depends on sound intensity and frequency. Yes. So how does it depend on time? Are shorter or longer sounds at the same, more or less loud? And it shows up that the loudness depends of the time. A longer time, the more loudness. You have temporal integration. Loudness comparisons of tone pulses of different durations. 25 test subjects. Okay. For equal loudness, for equal loudness, yeah, for equal loudness, 5 milliseconds tone needs 17 dBs higher level than 640 milliseconds tone. So if you have a longer tone, you need less sound pressure level. Yeah. Yes. Okay. I will just see. You have here loudness level. Yes. Okay. Yes. And you can record it in a loudness curve. So you have the straight line in this coordinate system, loudness level on first axis, loudness in sun in the second axis, is logarithmic build up. The second axis, loudness for a long tone is Stevens power law, yeah, and a straight line. And if you have 640 milliseconds, it's yeah, and you compare it with 5 milliseconds time duration, then you have to add 17 dBs more for the 5 milliseconds to get yeah, the same loudness level as 640 milliseconds. Yes. Okay. So yeah, for a fixed phone loudness in phone, you get a time duration makes the loudness increase. Or you can say at the same loudness level, you need more loudness. If the loudness is the same, you need more loudness level to if you compare small duration with time duration with longer time duration. Okay, it was a little bit clumsy. Physics, sum up, psychophysics, mapping between physical stimulus and response. Physical stimulus and response. That's psychophysics. Physical stimulus and perception response. Absolute versus differential thresholds. Just noticeable difference. Then we have a Weber fraction, delta I divided by I intensity is a constant, and Stevens power law that P, the perception could be is a the potence function I divided by I index 0 uploaded to E, where E can be, for instance, 0.3. Loudness perception. Loudness. What is loudness? It's a perceptual scale in zone. Loudness. What is the loudness level? It's relative to reference in phones. It makes the equal loudness contours. So loudness level is relative to reference in phones. Loudness recruitment and temporal integration. Loudness recruitment and temporal integration of loudness.